In this video, I wanted to talk to you about what's called the curl of a vector field. Roughly speaking, the curl of a vector field is a measure of how much the vectors in the field are spinning or swirling around. Now, the definition of curl is a little bit different depending on whether you're dealing with a two-dimensional vector field or a three-dimensional vector field. So let's start by talking about curl for a two-dimensional vector field. If you have a two-dimensional vector field, the curl of this vector field is a measurement of how much the vectors in the field appear to be swirling or spinning counterclockwise. So let's graph a couple of sample vector fields and let's see if we can predict whether the sign of the curl should be positive or negative or zero based upon this definition of curl as a measure of counterclockwise spin. So first up, we have the vector field, which is outputting the vector negative y, positive x. Okay, I just Googled graph 2D vector fields, and the first link that I found is this one for Desmos 2D vector field grapher. And so I've put in for our first component an output of negative y, and for our second component an output of x. And the corresponding vector field is graphed by computer here. Now looking at this vector field, you can see an absolutely clear swirling or spinning motion of the vectors in the field. Spinning, indeed, counterclockwise. So because these vectors are spinning in the positive direction, counterclockwise around the origin, we would say that this vector field definitely has positive curl. Now, by contrast, suppose that I went into the vector field and I made each of those components opposite what they were before. I can see that that reverses the direction of the spin. Now the vectors are spinning in the negative direction, clockwise around the origin. So because the vectors are spinning in the negative direction, they're spinning in some sense backward, we would say that this vector field has negative curl. Now let's have a look at this final vector field where the vector at position xy also has a formula xy. We can see that there is essentially no swirling motion whatsoever, right? There's no swirling motion. Instead, all the vectors are just blooming outward from this central location. They're being pushed outward from the origin. So this would be a vector field that has no circulation at all, and therefore this would be a vector field that has zero curl. Now, in each of these cases, the vector field was relatively simple, and the behavior, the swirling behavior of the vector field was consistent throughout the entire field. But it's totally possible to have a more complicated vector field that has slightly more chaotic behavior. Okay, so now I'm on GeoGebra. So if I look at the sort of top half of the graph, if I look up in this region, I can see that there's more of a swirl in the counterclockwise direction. I'm getting some pretty hefty vectors here toward the top of the picture, swirling counterclockwise. So there seems to be a sort of positive curl happening up here. However, if I look at the bottom half of the picture, the swirl is happening in the opposite orientation. The hefty vectors are here toward the bottom of the screen, spinning toward the counterclockwise direction here. So this is a vector field that seems to have positive curl on the top and negative curl on the bottom. This would be an example of a vector field that has a non-constant curl, a curl that can vary depending upon your position in the field. So we have the following formula that can be used to calculate the curl for a two-dimensional vector field. If you have a two-dimensional vector field whose first component is called P and whose second component is called Q, then the curl of the vector field is found by taking Q and taking its partial derivative in the x direction. So partial derivatives, remember partial derivatives from all the way back in phase 1 of the class. And then we're going to take p and we're going to take its y partial derivative, p sub y. And then we're going to subtract the two in the order q sub x minus p sub y. That is the curl of a two-dimensional vector field. Let's test this formula on the four vector fields that we studied graphically earlier in the lesson. And let's see if this formula makes sense based on the sign of the curl that we expected to get based on the picture. So if the vector field F was, it was negative y and then positive x, then the curl of this vector field would be equal to the partial derivative of q in the back with respect to x minus the partial derivative of y in the front with respect to y. So calculating these two partials, I would get 1 minus negative 1. I would get positive 2. And that is the positive curl that we expected to achieve based on the picture. If we do the same calculation for the second vector field, where we had positive y and negative x, the curl of this vector field would be the partial of the second component with respect to x minus the partial of the first component with respect to y. So this would be negative 1 minus 1. This would be a negative curl minus 2. And that's what we expected to see because graphically these vectors were swirling backward in the clockwise direction. If we do this calculation for the vector field x comma y, then the curl of that vector field would be the partial derivative of the second component with respect to x minus the partial derivative of the first component with respect to y. Now the partial derivative of y with respect to x is going to be 0. And likewise, the partial derivative of x with respect to y is going to be 0. So in this case, we get a curl of exactly 0, which makes sense because we found graphically that these vectors did not swirl at all. So we expected no curl in that case. And finally, let's do it for this more chaotic vector field. We have the vector field x squared minus y squared minus 4 and 2xy. And if I calculate the curl of that field, I would find the partial derivative of the second entry with respect to x, and I would subtract the partial derivative of the first entry with respect to y. And I would get, from that first calculation, 2y. And I would get from that second calculation, it looks like minus minus, so plus another 2y. Giving me a non-constant curl which is dependent on the value of y. A curl that is positive if y is positive, and a curl that is negative if y is negative. And that matched our observation from the graph as well. We saw in the graph that if we were dealing with locations on the upper half of the picture, where the y's of the positions are all positive, the swirl was in the positive direction as well. But if we were dealing with locations on the bottom half of the picture, whose y coordinates were all 0, the curl was backwards in this situation in the clockwise direction. And so that is matched by this result here. The curl is this particular function of y. The sign of the curl depends on the position. So that's curl for a 2D vector field. The curl is a scalar which measures how much the field is swirling or curling counterclockwise. Now let's move on to curl of a three-dimensional vector field. For three-dimensional vector fields, the curl is not going to be a single scalar anymore. For three-dimensional vector fields, the curl is going to be another 3D vector. And each of the components of the curl is going to give you different information about the vector field's behavior in three-dimensional space. The x component of the curl vector will communicate how the vector is swirling around the x-axis. Likewise, the y component will tell you how the vectors are swirling around the y-axis. And likewise, the z component of the 3D curl vector tells you how the vectors are swirling around the z-axis. Let's go ahead and have a look at some three-dimensional vector fields. Let's look at them graphically, and let's see what conclusions we might be able to make about the curl vector for these three-dimensional vector fields. And I'm going to start by experimenting on this first vector field, negative y in the x component, x in the y component, and 0 for the z component. So that's a negative y, that's x, and that's 0. Okay, so if I look at this vector field and I look at how the vectors are swirling around the z-axis, I can see that these vectors are swirling counterclockwise around the z-axis. So this vector field I would expect to have a pretty distinct positive curl in the z component. Now if I look at the vector field and I look at them as they're swirling around the x-axis, so let me look at it from the perspective of the x-axis. So I am not really seeing a clear swirling behavior around the x-axis. I don't see any swirl at all, really. They seem to be just moving sort of flat as viewed from the perspective of what is happening around the x-axis. So I wouldn't be surprised to find that the curl vector for this vector field has a 0x component. And likewise, if I view this vector field and I see what's happening along the y-axis, if I look down the length of the y-axis, I'm not really seeing any swirling around the y-axis here either. So I'm expecting probably the curl to have a 0 in both the x and the y components. Let's try this three-dimensional vector field xyz, and let's see what happens. So if I start by looking down the length of the positive x-axis, I can see no swirling or curling motion at all, right? I'm seeing the vectors flowing away from the origin, but I'm not seeing any swirling, either counterclockwise or clockwise. If I look down the length of the positive y-axis, I can see again no swirling motion. And if I look down the length of the positive z-axis, I can see again no swirling motion around that z-axis. So this is a vector field where I'm pretty sure that the curl vector will be 0 in every single component. I think that the curl vector for this vector field will actually be the 0 vector. And then for just another simple example, let's go ahead with 0 for x, z for the y component, and negative y for the z component. Okay, if I look at this vector down the length of the positive x-axis, so that the positive x-axis is coming out toward me, I can see a swirling in the clockwise direction. So I expect probably there's going to be a negative curl in the x component. If I look at that same vector field down the length of the positive y-axis, I'm not really seeing a swirling around that axis. If I look down the length of the positive z-axis, I'm not really seeing a swirling around that axis either. So this is a vector field that is probably going to have a curl with zeros in the y and z component. Now, of course, we have dealt with some very, very simple and straightforward vector fields here, but it's also very possible to have chaotic vector fields that have different curling and swirling behaviors depending on position. So it can happen that your curl is a non-constant vector. It's a vector that has functions in its components. So in other words, the curl of a three-dimensional vector field is another vector field, a three-dimensional vector that can have functions in its components. So that's a major difference between 2D curl and 3D curl. 2D curl is just a single scalar because there's only really one direction of swirling that you're dealing with. Whereas the curl of a 3D vector field is another vector field because there are several different directions in which you can swirl. Okay, so now that we have conceptually understood the curl, let's go ahead and write down the formula and the process that's used to calculate curl of a three-dimensional vector field. And in order to give that formula in a compact way, I'm going to introduce some notation, which is called sometimes nabla or the nabla operator. And the nabla is represented by this upside down triangle symbol that you encountered when you were studying the gradient vector back in the first part of the class. The nabla vector is a vector which contains the three partial derivatives for three-dimensional space. The partial derivative in the x direction, the partial derivative in the y direction, and the partial derivative in the z direction. Nabla, this upside down triangle with the vector on top, is shorthand for this 3D vector of these three partial derivative operators. Let me show you an example of how this operator is used as we give the definition of the curl of a 3D vector field. If your vector field is three-dimensional, and let's say that its entries are called P and Q and R respectively, then the curl of the vector field is equal to the cross product between this nabla operator and your vector field. Now, remembering the lesson that reviewed cross products and determinants, the cross product of two vectors could be found by taking the determinant of a 3 by 3 matrix. In the first row were the standard basis vectors I hat, j hat, and k hat. In the second row were the entries of the first vector in our cross product, which for nabla is partial partial x, partial partial y, and partial partial z. And then the final row in the matrix would be the entries of the second vector in the cross product, the x component of the field, the y component of the field, and the z component of the field. The curl is given by this formula. So let's do a few example calculations of the curl, namely with the simple vectors that we gave in these graphical examples that we studied a little while ago. Let's start by calculating the curl for negative y, positive x, and 0. So I'm going to fill up a 3 by 3 matrix with the basis vectors, with the partial derivative operators, and with the 3 entries of my vector field. And then I'm going to use the process that we learned for calculating determinants of 3 by 3 matrices to find the result of this determinant. So we're going to have something next to I hat, and then we're going to subtract something next to j hat, and then we're going to add something next to k hat, and those will be the components of the curl vector. Now, to figure out what goes next to I hat, we go into our matrix and we eliminate every entry that shares a row or a column with I hat, and we look just at this 2 by 2 matrix in the corner, and we take these diagonal products, ddy 0 and ddzx. What this is asking to do in this context is to take the partial derivative of 0 with respect to y and subtract the partial derivative of x with respect to z. So the difference between those two partials is going to be the x component of this particular curl. Same thing is true for the j hat portion of this determinant. I'm going to go into my matrix. I'm going to eliminate the row and the column containing j hat, and then I'm just going to focus on the diagonal products of the remaining 2 by 2 matrix. So this is saying take the partial with respect to x of 0, and then subtract the partial with respect to z of minus y. And that would be what is showing up here next to j hat in the curl. And finally, similarly for k hat, we're going to go into our matrix, we're going to eliminate the row and the column, and then we're going to take these diagonal products here in the 2 by 2 matrix. So what this is going to ask us to do is take the partial of x with respect to x and subtract the partial of minus y with respect to y. And that is going to be what shows up next to k hat in the curl vector. Okay, let's go ahead and simplify this. The curl of this vector field, the partial of 0 with respect to y is surely 0. The partial of x with respect to z is 0 as well. So this first component of the curl vector next to I hat is going to be nothing. Likewise, the partial of 0 with respect to x is nothing. The partial of negative y with respect to z is nothing. So I'm getting nothing here, and I have 0 in the y component as well. And then finally, we have the partial of x with respect to x. That's 1. Subtracting the partial of negative y with respect to y. That's negative 1. So our z component of the curl is positive 2. So we have, for the curl of this 3D vector field, no swirling around the x-axis, no swirling around the y-axis, and positive swirling around the z-axis, which is exactly what we expected to happen based on our graphical examination of this vector field. Let's do one more example of this calculation for this simple vector field 0, z, and negative y, just for one more example. These are kind of time-consuming calculations, so I won't do too many this time. We'll do 0, z, we said, negative y. Then the curl would be I hat, j hat, k hat, the 3 partial derivatives, and the 3 entries of the vector field. So the x component would be found by taking these diagonal partial derivatives. Now the partial derivative of negative y with respect to y is minus 1. And then I would be subtracting the partial derivative of z with respect to z. So I'm subtracting 1. Then the j hat entry would be, looks like 0. Derivative of negative y with respect to x is 0. Derivative of 0 with respect to z is also 0. And then in the z component, we would have 0 minus 0 again. So the curl of this simple vector field would have negative 2 in the x component and zeros elsewhere. And that exactly matches what we predicted graphically, right? The vectors were swirling clockwise around the x-axis, so we expected a negative value in the x component of the curl, and we expected zeros elsewhere because there were no swirling around the other axes. And that's exactly what we have obtained via this formula. So that's how the curl of 3D vector fields is calculated. To wrap up this video, let's just do one final calculation of the curl for a vector field that is not so simple to give us a curl that is non-constant. So we have our I hat, our j hat, and our k hat. We have our 3 partial derivative operators, and then we have the 3 entries of our vector field. So if I look at the entry that will show up next to I hat, giving me the x coordinate, this will be the partial with respect to y of negative 2y squared. So that would be negative 4y. And then we'll subtract the partial derivative of y plus z, that partial with respect to z. So that partial derivative will just be 1 from the partial derivative of z. So I have negative 4y, subtract 1. Okay, next we're moving on to the j hat entry, which we recall has an extra minus sign. Now we'll calculate the partial of negative 2y squared with respect to x. So that's going to be 0 from that. And then we're going to subtract the other diagonal, the partial of xy, as taken with respect to z. And since there are no z's here, that's going to be 0 as well. And then finally, the z component, the partial of y plus z with respect to x is going to be 0 because there are no x's there. And then we are subtracting the partial of xy, so that's going to be a subtracted x from that. So after simplification, the curl of the given vector field is another vector field whose components are given by negative y, negative 4y minus 1, 0, and negative x. So this means that the swirl around the x direction can vary. The swirl around the z-axis can vary, but there is always no swirl around the y-axis. That's really interesting, actually. Let me graph this vector field to see what it looks like. I want to see that. Hold on. Okay, here's the vector field in that problem. So let's look at it head on from the direction of the positive x-axis. Yeah, that makes sense. So it seems to be swirling approximately clockwise for most of it. And I guess that explains why we got that negative 4y minus 1, which is for relatively small values of y producing negative outputs. So that makes sense. Let's look at it from the direction of positive y. And yeah, truly, there's no clearly defined swirling motion from this vantage point that I can see. So I guess it makes sense that we got a 0 in that component. And then if I look at it from the vantage point of positive y, it's getting a little hard to read, that one actually. So that one is not, it's not as clear to me what the overall swirl behavior motion should be. The graph is a little too chaotic for me to parse personally. But this calculation shows that the swirl largely depends on the value of the x coordinate of your position in the vector field. Interesting.